Hello everyone, welcome to the lecture video number 8 of this video series on understanding FEA concepts with 1D example. My name is Vivek Varkal. In last video number 7, we try to understand weak form to FEA solution this workflow with example of one element discretization. Okay, so we also got the solution which we compared it with our analytical solution, something like this. Okay, so in this particular video we'll take again the same we'll take the example. We'll try to understand the weak form to FEA solution with example, but we'll take this time two elements discretization. Okay, so let's get started. Okay, so this is our problem. Unit length of road x equal to 0, x equal to 1. Okay, q0 and a equal to 1. If I discretize it into two finite elements, okay, this is element 1, element 2. Okay, then I will have three nodes: node number 1, node 2, node 3. Okay, displacement at node 1 is u1, displacement at node 2 is u2, displacement at node 3 is u3. So this is, I can represent this domain as a subdomains or assembly of two finite elements, something like this. Okay, so let's write weak form for this. 0 to 1 integral from 0 to 1 w dash u dash dx is equal to integral 0 to 1 w dx. Okay, and so next, it's weak discretized form. Okay, so this is 1, this will become 0.5 or 1 half 0.5, right? So I will write a weak discretized form as 0 to 1 by 2 w dash u dash dx plus 1 by 2 to 1. I should write 1 properly from now onwards. Okay, otherwise it will match with w dash and u dash. Okay. So w dash u dash dx is equal to, again, this 0 to 1 by 2 w dx plus integral 1 by 2 to 1 w dx. So this is our weak discretized form. Okay, let's find the FEA solution from this form. Okay, as you know, first thing is we have to assume the trial function or assume our solution. And as we discussed in last few videos, the u we can assume as a linear function. Okay, and trial function, the minimum requirement is it can be a linear function. And what is other thing? It is a discrete function, right? Okay, so okay, let's assume the trial function in form of discrete node solution and shape functions. So for element 1, okay, u subscript 1 is equal to n1 u1 plus n2 u2. Okay, and similarly w1 weighting function, as we said, as per Galerkin weighted residual method, we can assume weighting function same as displacement function because it is arbitrary. We can choose any weighting function. Okay, so it is n1 coefficients 1 w1 plus shape function n2 coefficient w2. Okay, and for element 2, okay, displacement in element 2 is equal to, as you know, it should be a function of this element nodes, so nodes 2 and 3. So n2 u2 plus n3 u3. Okay, and w2 is equal to n2 w2 coefficients w2 and w3 and shape functions n2 and n3. Okay, so it is if we just try to draw it. Okay, uh, 0 1 by 2 1. Okay, let's take, this is our u1, this is our u2, this is a u3. Okay, u1 u2 u3. Okay, so shape function n1 should be such that it is 1 at node 1 and 0 everywhere else. That means it should be 0 at node 2 and node 3. Similarly, for element 1, the shape function n2 should be 1 at node 2, remaining it should be 0. So it is n2. For element 2, again, shape function 2 should be something like this: 1 at node 2 and 0 at node 3. And this is also n2. Okay, and shape function 3, it should be 1 at node 3 and 0 everywhere else. Okay, so this is n3. Okay, same the same functions are going to be same for u1, sorry, u and w, right? Okay, and other thing is this n2 and this n2 are different. Okay, this is for element 1, this is for element 2. As you see, this n2 is this one, and this particular n2, it is in element 2, so this one. Okay, so we'll write save functions. Okay, so I'm just going to write it. And so n1, this is for element 1, n1 is equal to 1 minus 2x, n2 is equal to 2x. For element 2, n2 is equal to 2 minus 2x, and n3 is equal to 2x minus 1. Okay, so if you put this okay in this u, okay, you can say it is satisfying all this no solution. Okay, right? So as you say, like n1 should be 1 at node 1, everywhere else it should be 0. So if I say x equal to 0 here, n1 equal to 1, that means at x equal to 0 node 1, n1 is equal to 1. Okay, if I put 1 by 2 or 1 here, sorry, not 1, this is for element 1 only. So if I say node 2 x equal to 1 by 2 here, I get 0. So n1 is 0 at remaining nodes, that means node 2. So you can, these functions satisfy our requirement. Okay, okay, now we will substitute all this u and w function in our weak discretized form. Okay, so let's do that. Okay, so what I will do, I will give this 1. Okay, this I will give 2, this I number it as a 3, this is 4. Okay, so first I will take 1. Okay, term 1, term 1 in equation. Okay, which is this one, 0 to 1 by 2 w dash u dash dx. So I'm just no, focusing on term 1. So I'll just substitute everything. W dash is nothing but uh, I will say w is 1 minus 2x. Okay. This is for element 1, right? 0 to 1 by 2. So this is for element 1 only. Okay. So w is nothing but this one, n1 w1 n2 w2, and this n1 and n2. Okay. So 1 minus 2x coefficient 1 plus 2x coefficient 2. Okay. This is w dash. So this should be z. Sorry, dash. Similarly, u dash. Okay. So u dash is going to be the same. Okay. 1 minus 2x, but instead of coefficients, it's a solution u1. Okay. Plus 2x u2 and derivative of that into n dx. What is this? Okay. Dx. Okay. So if I take this one, now I know the boundary conditions, right? So u1 is equal to 0. We know w1 equal to 0. We know boundary condition u0 0. We will choose w such that w at x equal to 0 0, right? This means w1 equal to 0. Okay, and this means u1 equal to 0. Okay, so these two terms will become 0. Okay, now I will take term 2, which is same, but integral over 1 by 2 to 1 w dash u dash dx is equal to 1 by 2 1, and this time wx will be n2 w2 n3 w3 and n2 and n3 this one. Okay, so 2 minus 2x and 2x minus 1. So 2 minus 2x u2 plus 2x minus 1 n3. Okay, this is n3 u3. Okay, this dash into 2 minus 2x u, sorry, okay, let's take u2 u3. Here we will say w2. Okay, w2 plus 2x minus 1 w3. Okay, dx. So here no terms will get cancelled, so it will be, let's leave it as it is. Term 3 which is w dx over first element. Okay. So integral over first element w dx is equal to 0 to 1 by 2 integral w is L for element 1. Okay, so this is going to be 1 minus 2x, this one. Okay. This is for element 1. So n1 w1 plus n2 w2 w, and this is dx. Okay, and if I put boundary condition w1 is 0. Okay, so this term remains. Similarly, term 4 integral over 1 by 2 to 1 w dx is equal to 1 by 2 1. Okay, now it is this w 2 minus 2x w 2 plus 2x minus 1 w3 dx. So let's start again. Okay, term 1. Okay, if I just no I will just do integration here. Okay, uh, so this is gone. 2x w2 and dash. So what is that? 0 to 1 by 2. Term 1 is equal to this 2x integration will be x square. Okay, so it should be the differentiation. So 2x will be 2, 2w2, 2w2 into this 2u2, 2u2. Okay, and dx. So this further if I just expand this. Okay, so 4w2 u2 and uh, integral of 1 is x. So x with limits 1 0 to 1 by 2. So this will become 2 u2 w2. Okay, then term 2. Okay, so I'll just directly write down the term 2. Okay, you can try it on your own. Term 2 I get is w2 plus w3. If I do integration differentiation and apply the limits, it will be something like this: 2u2 plus 2u3. This is term 3, sorry, term 2. Then term 3 is equal to, I will get 1 by 4 w2. This you can take it as an exercise. Okay, and term 4 is equal to 1 by 4 w2 plus 1 by 4 w3. Okay, so now I will just club this. We know the equation term 1 plus term 2 is equal to term 3 plus term 4. Okay, so I will write weak discretization form after applying boundary condition. Okay, so it is going to be 2u2 w2, this one, plus this one, minus 2u2 plus 2u3 is equal to this plus this. So 1 by 4 w2 plus 1 by 4 w2 plus 1 by 4 w3. Okay, so this is my equation. I will just now solve this. Okay, so what I will do, I will just rearrange these terms. Okay, so that I will get the equation in form of uh, coefficients w2 and w3. Okay, so I'll just rearrange with w2, w2, w2. Okay, so this is going to be 2u2. Okay, this one, uh, coefficient for this is this one. So this plus will become minus 2u2, sorry, minus minus plus, so plus 2u2 minus 2u3. Okay, this minus plus minus, this is w2 coefficients. Okay, or sorry, coefficient w2, and it is this multiplier, plus I will take w3, okay, as a coefficients. Okay, so plus for w3 what it will be, uh, minus 2u2 plus 2u3, this one. Okay, and w3, okay, is equal to, here I will again write 1 by 4 plus 1 by 4, so 1 by 2 w2 plus 1 by 4 w3. Now I will write it as complete W2 in form of W2 and W3. So the final it will be 4u2 minus 2u3, and this one minus 1 by 2 W2 plus minus 2u2 plus 2u3 and minus 1 by 4 W3 is equal to 0. Okay. Now in order to solve this problem, okay, we know the properties of Wx. Okay, we know W is non-zero, right? It is arbitrary, but at the same time it is non-zero. So we can say this cannot be zero. These coefficients cannot be zero. That means these are going to be zero. So we have now two equations, minus 2u3. So these two equations, this one equation, this is second equation. So 4u2 minus 2u3 minus 1 by 2 equal to 0, and minus 2u2 plus 2u3 minus 1 by 4 equal to 0. Two equations, two unknown, u2 and u3. If I solve this, okay, I will not derive it here, but I will just directly write the solution for this. Okay, if I solve this, u2 uh, is equal to 3 by 8, and u3 is equal to 1 by 2, and u1 we know already, u1 is boundary condition, right? So for three nodes we have got the solutions u1, u2, u3, and as you know, we don't need to find w1, w2 and w3 because they are just coefficients. We are only interested in discrete discrete point solution, that means nodal solutions. Okay, and so this is our solution. Now let's try to compare this solution with our analytical solution. Okay, this time compare with analytical. Okay, so x x equal to 1 and x equal to 0, solution u. Okay, we know the solution is 1 by 2 at corner node. Okay. So our analytical solution is this one. So this is analytical. From last lecture we know the one discretization solution, right? So it is, okay, this is our one element solution, one element FEA solution. Okay, and now I will plot the two element which we just found the solution. Okay, two element solution. So node 1 it is 0, node 3 it is 1 by 2. So node 1 is 0, node 3 is 1 by 2, which is same. And for node 2, which is at the middle node, x equal to 0.5, it is 3 by 8. Okay, so this is node 2, 1 by 2, x equal to 1 by 2. The solution is 3 by 8, which will exactly sit here. Okay, so this is our node. node 2, node 3, and node 1. So and we know we have taken linear interpolation function or shape function. So the uh, within element the solution is linear. Sorry, it is not looking like linear. Okay. So it is linear, but you can understand this is a linear. And for element 2 also we have taken linear shape function. So this is, if we interpolate, it is again linear. Okay, so this is our solution. This we will say two element FEA solution. Okay. Now we'll just know discuss some observations here. Okay. This is analytical solution, which is exact solution. Okay. If we discretize the domain with one element, yellow color, we get the solution at the corner nodes exactly. Okay, exactly. Further, if we take two element discretization, okay, we discretize the domain in or rod into two elements. Okay, that means three nodes. The all nodal solutions we get as the exact solution. That means we get nodal solution as the exact solution, right? Or analytical solution. But if you see in between, okay, since it is a linearly interpolated, and we also assume that the solution is a linear interpolation from the nodes. Okay, so intermediate or within, I will not say intermediate, so within element solution, okay, is in linearly interpolated, and that is our assumption. And actually we are not interested in this within element solution. Okay, it is just for the purpose of plotting. Okay, otherwise our actual solution is nodal solution. Okay, and if you just see, we are wherever, no, from one element we went to two elements. Okay, we were able to capture the solution at the middle point exactly. Now if you further divide it into four elements, okay, you can obviously get the solution something like this. Okay, this one, this will match, then we'll get this solution exactly. Then this node will get solution, and this node will. So four, five nodes we will exactly match the solution. What is it meaning? Okay, as I refine the mesh, okay, I get closer to solution, get close solution. Okay, so and you know, like as we refine the mesh, okay, we capture this is FEF mesh convergence, you would have already known this. Okay, as we refine the mesh we get close to the solution. Okay, and if I just, you give one practical tips which I can recall now. Okay, if you have some FEA structure like this, okay, you may have what is this, let it be random. So you may have question how much to discretize, right? Means how fine or coarse element you want in your structure. Okay, so it is purely depending on your requirements, depends on your requirement. Okay, for example, for this structure, okay, uh, if your complete structure you think like it is a critical, okay, all the surface, where all the surface, I mean the stress you want to capture on an entire surface is a critical surface. Okay, you will refine the mesh in complete. structure with a, I mean you may mesh it with fine mesh. Okay, because you want the solution exactly at all the nodal locations. Okay, and for example, if I take same structure, okay, it doesn't look same, but let it assume it is a straight same structure. Okay, you feel that my this structure I am only interested in this location. Okay, this location only is my area of interest, and I want the accurate solution only in this localized area. Okay, then mesh it with fine mesh. Remaining locations you can mesh it with coarse mesh, so that you can take computational advantage. Okay, so this is one of the tips. There are many other tips, but this is what I feel I should discuss now. Okay, so this is more accuracy requirement is there. Okay, so I will use more refined mesh here. So with this, this is the end of the lecture video, and I hope this video and previous video, the examples with one element and two element discretizations are clear, and what we have seen, like we have compared the FEA solution with analytical solution. So let's see in our next lecture.